Is it a function?
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 8th grade, you should definitely be able to answer the question on the street, is it a function, by the end of this lesson. Couple things you want to make sure and do: take notes, follow through with the examples, focus on the vocabulary, and please, please, please have questions for me when you get back to class. Let's first recall what the definition of a function is. A function is simply a relation in which each element from the domain is mapped to exactly one element of the range. Exactly one, no more. So, for instance, if I had a mapping such as the following, let's say in my domain, I'll use D, I had 1, 2, and 3, and in my range, I had, let's say, 4 and 7, and 1 was mapped to 4, and 2 was mapped to 4, and 3 was mapped to 7, this would definitely be a function because each member or element of the domain was mapped to exactly one element of the range. Okay, so let's look at a few examples. We're going to determine if this relation is a function. First thing you want to do is basically observe each element of the domain. We've got 3, 4, 5, and 6, and notice that none of these are being mapped to a different or two different elements of the range, so we've got a function. In part B of example 1, you notice that our relation is actually placed in a different way. It's not listed as a set of ordered pairs like in part A, but in part B what we have is a graph. So if you notice, you can take a look at each of the ordered pairs and take a second. Is this a function? Why does it fail? It's not a function if you said no, and it does fail. And if you look at these 2 points here, you notice that the x term, or the element of the domain, in this case 1, is being mapped to two different elements of the range, which would be 4 and 1. So this fails as a function, not a function at all. In the last two parts of example 1, we saw what would be referred to as a discrete graph. In this case, we're looking at a discrete function. A discrete function is basically a function when it's graph that consists of points that are not connected. So below you can see a clear example of what a discrete function would be. Notice again it's a function because no x value has two separate or different y values associated with it. This next vocabulary word is the continuous function, and this is a function that when you graph it, it forms a continuous line or a smooth curve. Basically, the idea of continuity means you can draw the graph of the function without actually lifting your pencil or pen. A really important vocabulary term that you guys want to hold on to is a vertical line test. You're going to hear about this not just this year, but also when you get in high school. So definitely focus in a little bit on this. Honestly, reading the definition is cool, but seeing it in practice is better. So after we talk about the definition, we'll look at a couple examples. Vertical line test is just a test used to determine if a graph relation represents a function. If a vertical line is drawn on a graph of a relation and it hits the graph more than once, then the relation is not a function. Let's take a look. For example 2, we're going to determine whether each function that we see here represents, or whether each relation or graph represents a function. And we're going to do that using the vertical line tests. So if we look at example 2, part A, we have what we should recognize as a parabola. If you don't remember, we'll go over that soon. I'm going to take my blue pen and I'm going to draw vertical lines through the graph, vertical lines straight down. Notice that no matter where I draw these vertical lines, I'm only going to hit the graph at one individual point. This lets me know that indeed this is a function. If I try that with the second graph, notice what happens. So again, I'm going to go around drawing my blue vertical lines, and I'm hitting each time, practically every time, I'm hitting the graph at two distinct spots. This lets me know that for each x value, or for several x values, there are two y values that are associated with it. Therefore, this is not a function. So the vertical line test can tell me, given a graph, whether or not I have a function by simply drawing vertical lines across the graph. Example 3 introduces us to the idea that equations can be functions. So we're going to start off with this equation, negative 3x plus y equals 8, and we're going to try to figure out a way to determine whether this equation represents a function. The first thing we're going to do is set up a table of values. We're going to plot those table of values. After we get a graph of the function, you guessed it, we're going to use the vertical line test. The first thing we'll do is create a table with at least 4 arbitrary x values. We're going to take those x values and we're going to plug it right into our equation and see what the corresponding y value is. So, if x is going to be negative 1, negative 3 times negative 1 plus some value y will equal 8. Doing the math, I will get, let me use a better color, negative 3 times 1 is a positive 3 plus y equals 8. So what number could that be? I'm sure you guys guessed it. The answer is 5. We'll take the next value and do exactly the same thing using the original equation. So now we're going to do negative 3 times 0 plus y equals 8. Negative 3 times 0 is 0, plus y equals 8. Clearly, y is 8. Following right along, negative 3, let's get that. Negative 3 times 1 plus y equals 8. Negative 3 plus y is 8. Can anybody guess what that is? Think about it. My guess is that number is 11. If I add 11 plus negative 3, I'll get 8. Finally, I'm going to plug 2 in to the equation here, and I'll get negative 6 plus y equals 8. And to figure out what that value is, some of you are familiar with the method of doing the opposite on either side of the equal sign, and so I get y is equal to 14. So I'll have a 14 right here. With these points, I'm going to plot them and see whether or not I actually have a function. Okay, with our graph in place, we can see that each point from our ordered pairs in our table is perfectly represented right here in our graph, and then we simply connected the lines. So is this a function? Simply doing the vertical line test, we see that indeed each of our vertical lines only hits once, so indeed it is a function. This equation represented a function. The final vocabulary term that we'll talk about is function notation. This is also something that you're going to see again and again, so do try to get yourself used to it. Now here's the deal. It seems really off-putting. I remember feeling really uncomfortable with it the first time I saw it, but what I want you to know is that function notation, writing f with an x next to it in parentheses, I'll call it f of x. Writing that is the same thing as talking about y. So here it is. Function notation is simply writing an equation, like y equals 2x plus 3, as f of x equals 2x plus 3. This is considered function notation. Not a big deal, and as a matter of fact, it becomes quite handy. I'll show you what I mean. So if I were dealing with this function here, y equals 2x plus 3, and I wanted to know what is y, let's do it this way. I wanted to, let's say, find y when x is 4. You guys would know to plug 4 into that equation. And if you could do a quick mental math, you'd plug 4 in, you get 2 times 4 is 8, plus 3 is 11. So in this case, y is equal to 11 when x is 4. But with function notation, we have the ability to do something a little bit simpler. So instead of saying what's y when x is equal to 4, we can simply say what is f of 4, which is code for what's y when x is equal to 4. And I would write f of 4 is equal to, what did we say last time? 11. Okay. Okay, so here are two examples, or one example, example 4 with two sections, where we can really kind of explore this idea of function notation. So remember, this up here is really just y equals negative 4x plus 7. And this is basically saying, what is y when x is equal to 2 in this equation? So what I'm going to do is replace every x in the equation with the number 2. So f of 2 is equal to negative 4 times 2. X is 2, so that's what I'm doing. I'm just replacing it, plus 7. Simple math gives me that this is negative 8 plus 7. And if you guys remember, that negative plus that positive 7 is going to give me negative 1. So the answer to this is negative 1. F of 2 equals negative 1. Let's try another one. Here, we're asked to figure out what is y when x is negative 3, and then add 1 on to whatever that is. So f of negative 3 plus 1 is basically what's y when x is negative 3, then add 1 onto whatever that is. So again, we're going to replace the function, in the function, we're going to replace x with the value here. So we have negative 4 times negative 3 plus 7. That's all the function. And then I've got this 1 to add on. Let me actually circle that in red. I'm going to add this 1 on because that's the additional part they asked me to do. So negative 4 times negative 3 is going to give me a positive 12 plus 7 plus 1. When I add all of that together, I get 20. So this is equal to 20. Okay, everybody, I added on one more example. I know it seems like a lot, but you've done so far to stick with me, so one more won't hurt. All right, so here we have another function, but it looks like it's kind of different. We don't have x, we don't have y, and we don't have the f of x that we had just been getting used to. So what I want you to see is that sometimes functions can be written like this. Instead of f of x, we've got g of t, but notice that t is all in here. And again, we're asked to find what is the function value when the variable, in this case t, is equal to 0, and here what is the function value when t is equal to 1. We would do exactly what you think we'd do. In this case, let's use the brown one, g of 0 is simply negative 16, 0 squared, notice I'm putting 0 in for t, plus 32 times 0 plus 5. This is an easy one because 0 times anything is 0. These guys go away, and I simply get that g of 0 is equal to 5. This next problem, analyzing g of, let's leave that one highlighted, analyzing g of 1, we're going to plug 1 into the equation and we'll see what we get. So g of 1 is equal to negative 16. Notice I'm plugging in 1 for t, quantity squared, plus 32 times 1 plus 5. 1 squared is simply 1, so this becomes negative 16 times 1, which is just negative 16, plus, this is just 32, and then I'm going to add 5 to that. When I add negative 16 plus 32, I get 16. When I add 5 to that, I get 21. So g of 1 is equal to 21. All right. That's enough examples for now. I'm going to give you guys a few problems that I think you should try out on your own to see if you really understood the lesson, and then we'll talk about it when we get in class. Take care. Okay, guys, here are some problems to try. Pause it, try them, and I'm going to put the answers down. So you can pause me now. Okay.